Alright, so in this video, we'll be looking at some gas collected over water problems. And so this is one of those classic problems that you'll see in general chemistry as well as in AP chemistry. So it's important that you can solve these types of problems, as there are going to be some free points for you. But getting right into it, when you're looking at gas collected over water, right? For example, let's say by bubbling hydrogen into an inverted container, right? That gas that you're collecting isn't pure. And what I mean by that is that it's going to be a mixture of your gas plus your water vapor. So that total pressure that you measure, or rather in these types of problems, you'll be provided with a total pressure. And that pressure that you're given is not just the pressure of that gas. We could write it out, right? That total pressure, let's call it P total, is going to be the pressure of the gas, right? In our hydrogen bubbled over water example, it's going to be the pressure of hydrogen, but it's also going to include, so it's going to be the pressure of the gas plus the pressure of your water vapor. So this is what we're looking at, right? The total pressure that you're given is the pressure of the gas plus that of the water vapor, because we said it's going to be a mixture, right, that you're collecting. And so in order to find the pressure of the gas alone, right, the pressure of that gas alone is just going to be equal to your total pressure minus the pressure of your water vapor, which again, remember, will be varying dependent on the temperature. So keeping this in mind, let's just look at a couple of problems. All right, so we're given that we have a sample of oxygen that is collected over water at 25 degrees Celsius, and the total pressure is 750 milligrams of mercury, and the water vapor pressure at this 25 degrees Celsius is 24 milliliters of mercury. And we had to find the partial pressure of oxygen. Well, looking at that, the concept that we were just talking about, right? The idea that this gas that we're collecting is a mixture, we know that this total pressure that's provided to us is going to be, this total pressure is going to be the pressure of the gas. Specifically in this case, our gas is oxygen, so we can say it's that partial pressure of oxygen plus the pressure of our water vapor. And so we can say that this 750 milliliters of mercury is going to be our partial pressure of oxygen plus our 24 from our water vapor. So we now know that our partial pressure of oxygen is just going to be 750 minus 24, or 726. And so this is going to be the answer here. And so this is, again, not really a full-out worked-out problem. It's just to demonstrate, proof of concept, or to demonstrate the idea that our total pressure is really going to be a mixture of these two different pressures. And this is often going to be the first step, or at least one step that students often forget to do when they are working with these types of problems. So that's why I just wanted to have a separate, problem here just dedicated to looking at that situation. All right, now let's look at another problem. So we're given that hydrogen gas is collected over water at 20 degrees Celsius. The total pressure is 740 milligrams of mercury. Milliliters of mercury. And this volume is collected in 450 milliliters. And the vapor pressure of water at 20 degrees Celsius is 18 milliliters of mercury. Find the moles of hydrogen gas collected. All right, so before we get to the moles part, let's just first figure out how much hydrogen exactly that we're dealing with. And we know that we can do this by just taking our total pressure, which is provided to us, and we know it to be the pressure of the gas plus the pressure of the water vapor. And so we know that our total pressure here is 740, which is going to be the pressure of our hydrogen gas plus our water vapor, which again we see at 20 degrees Celsius exerts a force of 18 milliliters of mercury. And so the partial pressure of our hydrogen gas in this problem is going to be 740 minus 18, or 722. And it's important that you keep track of your units, and I'll get to exactly why in a minute. So we're seeing that we have 722 milliliters of mercury. So that is the pressure that our hydrogen gas is exerting. So this is kind of a metric that we have for our hydrogen gas. And now we have to go from this pressure to moles of hydrogen gas collected. How do we do this? Well, I'm hoping you guys are familiar with the concept of the ideal gas law. If you aren't, just a very brief overview, the ideal gas law, which is PV equals nRT. Okay? So we're going to basically be using this formula for a number of different gas-related problems. And it's because we're basically able to relate our pressure, volume, moles, and temperature with one another with the help of our constant here, which is basically allowing us to have this established relationship between these different quantities. And so, given our pressure and our volume and our moles, we can solve for our temperature. Given our temperature, we can figure out, or given our temperature, moles, and volume, we can figure out our pressure. So if we have any three, because R is a constant and is always the same, we can figure out the other. And so because of this, it's a very powerful tool, and is also what we will be using in this problem, because we're trying to find our moles of hydrogen gas. We have pressure, and we have our volume here given in 450 milliliters. We know what R is, and we have our temperature. We know that this is occurring at 20 degrees Celsius. And so, by isolating for N, which in this case is moles, right? In PV equals nRT, N is standing for our moles. So isolating for our moles gives us N equals PV over RT. And so this is basically what we're going to be using in order to figure out the moles of hydrogen gas that has been collected. And so while we are here, I'm just going to clear this up. Let's keep note of these numbers in our mind for a minute and just go a little bit more in depth about each of the variables here, or parts of this ideal gas law. And so we already know, we talked about how P stands for pressure, and our pressure here, our pressure is going to have to be in units of ATM. So again, this is important, right? Our units with which we are dealing with when we're using the ideal gas law is very important. If we do not use the correct units, we will get the wrong answer, and we can't actually use this very helpful formula. So when we are dealing with pressure, it has to be in ATM. So if we're not given the pressure in ATM, we have to convert to ATM. So our volume also needs to specifically be in liters. So this volume must be in liters. N is our moles of gas. There are no other units for that, it's just moles. Our R here is the gas constant. The gas constant. And it has a value of 0.8206. Again, depending on the formula sheet that you're given, it may have more or less decimals, but it's approximately 0.08206 liters times ATM over moles times Kelvin. And finally, our temperature has to be in units of Kelvin. Temperature, and that is in units of Kelvin. So let's keep these things in mind and move forward with the problem. So firstly, we see that we got our pressure, the pressure of our hydrogen gas, but that is in units of milliliters of mercury, right? That is in units of milliliters of mercury. We said that we have 722 milliliters of mercury of our hydrogen gas. So the first step is, if we want to use our ideal gas law, is to convert this from milliliters of mercury into ATM. So how do we go about doing this? Well, we simply have to divide by 760, or setting it up stoichiometrically, we can say that 722 milliliters of mercury, and basically 760 1 ATM, canceling out our units, gives us our answer in ATM of 0.950 ATM. So this is the pressure that we will be dealing with. Let's just keep that in mind. I'll write it up top. So our pressure is 0.950 ATM. What about our volume? Well, we're given our volume here as 450 milliliters, but if you can remember, we know that when we're dealing with the ideal gas law, our volume has to be in liters. So let's convert this 450 milliliters into liters. We know that there's 1,000 milliliters in every liter, so we have 0.450 liters. Next, well, we already have our gas constant, so there's nothing we have to deal with there in terms of any conversions. But we have to convert our temperature finally. Here we're given our temperature in units of degrees Celsius, but if you remember, our temperature must be in degrees Kelvin. And so first, let us convert that. And so basically, how do we do that? Well, to go from degrees Celsius to Kelvin, we simply have to take our temperature in Celsius and to it add 273. And this is going to give us our temperature in degrees in Kelvin. So we basically take 20 plus 273, giving us 293 Kelvin. Right, so our temperature is 293 Kelvin. And now we have enough information to just plug and chug, getting our answer. So we know by manipulating this algebraically that our moles is PV over RT, which is going to be equal to 0.950 times 0.450 divided by 0.08206, which is our gas constant, and our temperature, 293 Kelvin. And just working this out gives us an answer of 0.0178 moles of hydrogen gas collected. And this here is going to be our answer. Alright, let's look at the next problem. We're given a sample of methane gas is collected over water at 27 degrees Celsius. The total pressure is 765 millimeters of mercury, and the volume is 620 milliliters. The vapor pressure of water at 27 degrees Celsius is 27 millimeters of mercury. Find the mass of methane collected. Alright, so if you want, take a minute, pause the video and try to work this out yourself. And I assume you've given it a try, and now let's go through it together. Alright, let's start again, like we always do, with our total pressure and isolating to find the pressure of methane alone, the partial pressure of methane. Well, we know that our total pressure is going to be equal to the pressure of our methane gas plus the pressure from our water vapor. And so, the pressure of methane is just this total pressure minus that from the water vapor, and so we're just going to be doing 765 minus 27, giving us 738 millimeters of mercury for our methane gas. That is the partial pressure of methane. And so what do we do next? Well, what are we trying to find? We're trying to find the mass of methane. And so really, if you want to kind of have a roadmap of what we're going to try to be doing, we're going to be trying to go from this. We're trying to go from our pressure to our moles like we did last time, but then from moles to mass. So this is not something that should be too difficult. We're just going to be needing to use the molar mass here. This is something you should be familiar with. And so it's just one additional step compared to what we did last time. So we're going to be going back to our handy ideal gas law for this problem as well. First, remember, the ideal gas law requires us to have units of ATM for pressure. So we're going to have to convert this 738 millimeters of mercury into ATM. Canceling out these units gives us an answer of 0.971 ATM. So this here is going to be our pressure of methane. Let's just make some space for the next steps, and I'll just keep track of that pressure off to the side. So our pressure is going to be equal to 0.971 ATM. What do we need next? Well, let's just write out our ideal gas law real quick. PV equals nRT. Just like before, we're going to be trying to isolate for that our moles. So our moles is going to be equal to PV over RT. We just found our pressure. We need now our volume and our temperature to move forward. So let's just start with our volume. We're given that we have a volume of 620 milliliters. But remember, the ideal gas law requires us to deal with units of liters. So let us convert milliliters to liters. We know again 1,000 milliliters in every liter. So we have 0.620, not milliliters, 0.620 liters. This here is going to be the volume, 0.620 liters. All right, and now we're going to be needing our temperature. Remember, temperature, again, here is given to us, is 27 degrees Celsius. We need that to be in Kelvin. So how do we convert from degrees Celsius to Kelvin? We just take our temperature in degrees Celsius and to it add 273. And that will there just convert our answer into, or convert our temperature into Kelvin. So here we're dealing with 300 Kelvin. That is the temperature. 300 Kelvin. Now that we have all this information, we can simply plug and chug. So PV equals nRT. So N is just PV over RT. This is going to be equal to 0.971 times 0.620 over our ideal gas law, or over our gas constant, 0.08206, times our temperature, 300. And this is going to give us an answer of 0.0244 moles of methane. But we are not done. Unlike the last problem, we are not solving for moles. We are trying to go from our moles now, finally, if you remember back to that roadmap, we were trying to go from pressure to moles to finally mass. What is the mass of methane? So how do we go about converting or going from moles to mass? Well, we need that molar mass. So let's quickly calculate the molar mass of methane. The molar mass of methane is just going to be 1 times 12.01 grams per mole, 12.01 grams per mole, the molar mass of our carbon, plus 4 times the molar mass of our hydrogen. And this is going to give us an approximate, molar mass of 16 grams per mole. This here is our molar mass for our methane. So now, simply, we're going to go from our 0.0244 moles of methane that we just calculated using our ideal gas law. We're going to say that 1 mole of methane, 16 grams, right? We just calculated that molar mass. Canceling out our units of moles is going to give us an answer of 0.390 grams of methane collected. This here is the answer to this problem.